Hey there, everybody. Welcome to a fantastic physics day. We are starting a brand new topic, and the most exciting part of this is we get to work on the back of the equation sheet. So we have pretty much worn out the front completely. We get to flip over to the back now, which is very exciting. So grab your equation sheet, and we're going to be on the waves and optics part. So once you grab that, start things up again. Also, what I would suggest very, very strongly is be sure you're writing this stuff down, because I'm going to let you use your notes on the quizzes. And the quiz is going to refer back to several parts on these notes. Alrighty, I'm going to assume you got your stuff, and let's get started. So there's waves we're going to talk about today are called mechanical waves. And here's the big key with mechanical waves. Mechanical waves always travel or go through something. So we can have waves on the ocean or water waves. We could have waves on a slinky. We could have waves on a string. We could have any kind of waves you want. As long as they're going through something, they're called mechanical waves. All right? Now there's going to be a kind of a special thing with light later on, and while light can go through things, that's a different kind of a wave. So we're going to get to that later, though. All right, let's get started on this stuff. Here I've got a string, and the green part there at the left side, I wiggled up and down and made a wave travel down it with a velocity. So I want you to notice something here. The wave is going from the left to the right, but the piece of string right here moved up, and in just a little while it's going to move back down. And then a little while later, what's going to happen is the string is going to move up like this and come down. And what that's going to make happen is this part of the wave is going to move up and down. All right? So here's a great example of the string is what the wave is traveling through. Sometimes we call that the medium. And the wave itself is moving along that string. Now, very important. This kind of wave has a name. It's called a transverse wave. And a good way to remember this wave is by remembering the trans part. Trans means sometimes across. So the wave is moving up and down. I'm sorry, the wave is moving left to right. The string is moving up and down. So the direction the string moves and the direction the wave moves are perpendicular from each other in this kind of wave. We have one other kind of wave which we did in a slinky, okay? And if you push in the end of a slinky after it's been stretched out, you make a different kind of wave. So notice in this one, the wave is moving from left to right. The slinky itself is moving left to right as well. And we have a little compression in there. Okay? This one is called a longitudinal wave. There we go. I think I got that right. Longitudinal. All right. So longitudinal wave, turns out that the medium moves in the same direction as the wave, in this case left to right for both of them. Back up to the transverse wave, the medium moves perpendicular to the direction of the wave. All right? So just some qualitative things you got to get your head around. Alrighty, let's move on. We swung pendulums, and we had springs wobble back and forth quite a bit last semester. So our pendulum is moving there, our spring is moving there. I'm going to put a piece of paper underneath them. I'm going to attach a pen to each one of them, and I'm going to pull the paper along at a constant rate. And basically we're going to make a sine or a cosine wave, whichever you want to call it. The shapes are the same. Okay, I just wanted you to kind of see where we started with this. So this connects back to first semester. We're not going to do very much connections. We're going to move forward, but I just wanted you to see it. Let's take one of these graphs and turn it sideways like this, and let's label a few things. All right. You've seen these before, but I want to review so that you'll see them again and get them rattling around back in those brains. All right, if I pick a spot anywhere on the wave and go to the same spot, this is called the wavelength, and that is a lambda. That's a funny little, it's almost an upside down Y sort of, kind of, but it's being bent over by the wind. Maybe a little sexy there. And the units on lambda are in meters. Now, the cool thing here is I can choose any point on the wave I want to make a lambda. For example, I could choose this spot here and go all the way over to the same spot, and it turns out that's lambda as well, exactly the same. I can choose the top of the wave, go from here over to here. That's lambda as well. Because it's a periodic or a repeating function, it's always going to be the same. Okay? Lambda, measured in meters, wavelength. Next one, we're going to have amplitude. Amplitude goes from the center of the wave, or where the medium would be if it wasn't doing a wave, okay, to the top or to the bottom of the wave. All right? Both of those are going to be the same. They're just one's to the top of the wave and one's to the bottom. Amplitude. Again, the units on amplitude are meters, or it's a distance. All right, so far so good, piece of cake. A couple more words. I'm not going to label these because things are getting a little full, but here's what I want you to write down. The top of a wave right up here is called the crest of the wave. That one's pretty easy. And the bottom of the wave down here is the trough. Okay? You're going to see that a little more in a little while when we get into standing waves, but for now, we're just going to leave it at that. All right. We have amplitude, we have wavelength. Let's do one other one. If we stand in one spot, all right, I'm going to go ahead and draw us standing and looking right here. If we look at that and we take the time it takes for one wavelength to go by, so in this case it would be from the trough to the trough, all right? So you need to write that down. The time from one spot to the same spot on the wave, the time for one wavelength to go by, we're going to call that the period, or T. All right? The name for it is going to be period, and that's going to be measured in seconds. Now notice I wrote down period for this. I didn't write down the word amplitude or the word wavelength. You definitely need to label those. Okay? The period in seconds. Now there was another one we did when we were swinging pendulums and springs and stuff, and that was the frequency. Okay? You need to write the word there. And frequency is measured in 1/seconds because the frequency equals 1/the period. So while the period is how long it takes for one wavelength to go by, the frequency is how many wavelengths go by in one period. Now notice, if we rearrange our equation over here, we can say 1/the frequency equals the period. That's pretty straightforward, not too bad. Alrighty, so now that we're in waves, we have to do one more new little bit of math. Sorry about that. But somebody asked me, they said, hey, tell me about the velocity that that wave goes by. How fast is that wave moving? All right, let's see if we can figure this one out. Velocity is distance divided by time. Let's choose an easy distance to measure on the wave. Let's choose 1 wavelength. Okay? So how long does it take for 1 wavelength to go by? Well, hey, golly Wally, I just told you that. 1 wavelength goes by in exactly 1 period. Fantastic. Now what I want you to do is trade period for frequency. Okay? And the frequency is 1 over the period. Well, check it out. It's already something over the period, so I can just write it like that. Velocity equals a wavelength times the frequency. Look on your equation sheet. It's the top equation in waves. All right? And what we're going to do is I want you to label that velocity of the wave and label the frequency in the wavelength. Okay? All righty. So now, one last thing before we talk about the quiz. I copied our wave picture above, and I just wanted you to see that the top one is a transverse wave, bottom one is a longitudinal wave. Now, if I mark a couple spots here, in the longitudinal wave, right in here would be squished, okay? We might have compression there. That means right here we would have stretch. Notice something. In the transverse wave, the squish lines up with it swinging one way, the stretch lines up with it swinging the other way. All right? So, right along here, where our transverse wave is in the middle, at the green spots here is where we would have the spring that is stretched just its normal stretch. All right? I just did this so you can kind of get a picture of how a transverse and a longitudinal wave would line up. The good news is this. Check this out. We can measure a wavelength in our longitudinal wave. It's the same wavelength as in the transverse wave, from top to top or from squish to squish. We could also do it from stretch to stretch. Now, measuring the amplitude gets a little tricky, so we're not going to do that. But I just wanted you to see how we would get a wavelength with this. So I could give you the wave equation, right? And you have the wavelength, you could measure the period, and boom, we could get the velocity. All right, I'm talking way too long. Here's your quiz for tomorrow. Your quiz. I'm going to give you a wave, and you need to label everything you can on it. Second thing I'm going to do is use that equation for the velocity of a wave, and I'll give you a little story problem, and you'll have to plug and chug, and it's a piece of cake. Just, there's not even hard math. Sorry about taking so long. Hope you have a wonderful evening, and we'll see you tomorrow.